Say what? You are still chemists. Yes, you are still chemists. No worries, okay? The first midterm is always a little bit a pain in the bum, okay? But things will get better. I told you, things will get better. So it's looking up from here. It's looking up from here. The keys are also on the class website. Please check them out. You can see what the answers are. And if you want to look at your exam, then you can do that. Turns out, Austin has all the exams next week, right? So if you want to see your exam, you can go to his office hours. I think after that week, probably I will have them, because I think I should collect them. And then after that week, you can come to me to talk about your quiz. We don't give the copies out to you for you to take home, because that leads to all kinds of problems. So that's why we keep the exam, but you are welcome to have a look if you want to. Okay? All right, so any questions from you guys? Concerns? All right. In that case, I'll just move on with some of the things that we have been unveiling the last couple of lectures, and they have to do, of course, with the wave functions of the hydrogen atom. Okay, so because we have found them now, we solved the Schrödinger equation, and we studied last lecture, the probability density along the radial coordinate, and from that, we also looked at the energies, and we have now a pretty good idea of the states in which the electron can sit, and that those states actually correspond to the orbitals that we are so familiar with. Okay, so that is a great leap. Now, this lecture and next will be about another very important ingredient that we haven't touched on at all. Okay? And in order to get to that point, it's actually the reveal is on the last slide, but in order to get to that, I have 5 slides prepared for you today. 5, but it will take about 50 minutes or so, okay? So let's do that. What is the story? The story goes back to one of the concepts that we have been playing with and trying to understand, really, and that's about angular momentum. Okay? Angular momentum is, of course, very important. And we have seen angular momentum of the electron when it has a wave function. Some of these wave functions have actually an angular momentum that is non-zero. So how do we think about this? So let's think about a property that's called orbital angular momentum. We know orbital angular momentum is related to a quantum number, namely L. Okay? The L quantum number is called the orbital angular momentum quantum number. Okay? So we have to kind of make ourselves familiar with that. And also, ML, the magnetic quantum number, also relates to angular momentum. Okay? So today I'm going to have a closer look at that, trying to kind of really get a better understanding of this, and maybe generalize this concept, and then apply it to something else. So here it is. Think again about an electron that is now confined to a ring. Okay? And the ring has a radius r. Now this r, I can write as a position vector, which is given like this. Okay, so I have a value along x, value along y, and z. And so the x, y, and z coordinates here are indicated by I, j, and k. That's just x, y, and z, the coordinate, the axes, the directions. The values x, y, and z are how much you have along each of these coordinates. Okay, so this is a typical way to kind of describe a position vector. Now, if this thing is on the ring and it goes, let's say, counterclockwise, then it has a momentum. And at this particular point, indicated by r, the momentum is basically like this. Okay? So that is p. But p is also a vector, as you can see. So let's write that down. Here it is. P is also a vector. It has projections along the I, j, and k directions, which is x, y, and z directions. And the values are px, py, and pz. In this case, it moves in the xy plane, so pz is 0. But px and py are not. Okay, so angular momentum, orbital angular momentum, is defined, and we have seen this before, because we had electron this, as this. Okay? The orbital angular momentum of, let's say, an electron here is L, which is also a vector, equals R, and then the vector product with P. Okay? So that is basically a definition of angular momentum, and there's nothing quantum mechanical about this per se. This is just very general. Okay? If you open up a physics book, you'll see this formula right there. So how do you calculate this angular momentum vector then? Well, we have this right-hand rule. Here it is. You can use your hands. Okay? So you have A, vector B. Now the result is another vector that points kind of in an orthogonal direction as defined by the right-hand rule. So this L would here be a kind of A vector product B. Okay? That is the direction of L. And the way to calculate that is this. Okay? This is the formula we have already had on the screen not so long ago. So for the example sketched over there in the left corner, you can see since the particle moves only in the xy plane, the angular momentum actually shoots up or points up. Okay? So the angular momentum is a vector. In this case, the vector points along the positive z-axis. That's indicated by the blue arrow. But I can make this more general. It doesn't have to be confined to the xy plane. Okay? The motion can be in any kind of direction, really. And therefore, L can also be in any direction. It doesn't have to be always along z. It can be in any direction. L can point in any direction. It's a vector with a magnitude and a direction. Let's calculate that in general. This is how you do it. Okay? Hopefully I don't have to explain that. But this is how you calculate a vector product. Along each of the coordinates, I, j, and k, I can now see how much I have along each of these coordinates, indicated by these terms between parentheses. The terms between parentheses I can give names. Namely, the first one I call Lx, the second one Ly, and the third one Lz. So these are really just how much I have along each of the coordinates, and that defines the vector L. Because it's a vector, and this vector has projections along x, y, and z, indicated by this expression here. Okay, so just to kind of like have a picture in mind, we have looked at this green circle here, or the green plane here, which is x and y, in which case the vector points up for angular momentum. But what if I'm actually on this ring, this guy? Okay? So if I actually go this way, all right, then my angular momentum points along x, like that. Or if I'm actually moving on this, the black line here, the black circle, like this, and it points out of the screen, angular momentum. So angular momentum can point in all directions, really depending on in which way you rotate. Okay? What way you rotate on this sphere determines the direction of your angular momentum vector. Okay, so these components then, Lx, Ly, Lz, I can calculate with these expressions. And this is again very general. This has nothing to do with quantum mechanics. This is just also true in classical mechanics. Okay. So now let's do something quantum then. Let's take this Lz component, and here it is. This is what the Lz component is, and I put little hats on all of them, and therefore now it's an operator. Okay? So the operator for angular momentum, its projection along the z-axis, is this: x times py, y times px, where all of these guys now are operators. And we have seen a couple of lectures ago that this is simply represented by this form. H bar over I d d phi, which allows us to calculate its angular momentum. Angular momentum of a wave function can be calculated with this expression, which is only a function of phi here. So we also talked about the magnitude, because what this operator does, it tells me what is the projection of your angular momentum vector along the z-axis, and the answer is basically provided by that operator. But what if I'm interested in the magnitude of angular momentum? Remember, this is a vector, it has a direction, and it has a magnitude, okay? So we have now some information about its direction, but only the projection along the z-axis is what we know. We don't know the projection along x and y yet. Okay, so we have one projection, so we know something about the direction of this vector. We don't know what the magnitude is, and I'd like to know what it is. So how do we do that? Okay, well, if you take the vector and multiply it by itself, okay, you get something like that. That's what you're doing. Okay, so this is just the expression of the vector squared, and I'm going to write that out. What I'm getting is each of these terms, just its square, and then I get all the cross terms. Okay, that happens when you take a square of something. If you take a square of a sum, you get every element in the sum is squared by itself, and then it's combined with all the other guys. Okay, that's what you see here. Now, the position vector I, j, and k, if you square those, you get 1. Actually, this k should have a square on it too. Okay, it should be k squared. Every unit vector, if you square it by itself, it's 1. So that's good. And if you square the unit vector with another unit vector that's not the same, it's 0. X and y are orthogonal. Okay, we know that. So all of these cross terms are happily 0. So, if I square the vector with itself, I get a result, and this result is not a vector, it is actually a number. It's basically the square of all the components along x, y, and z. So that is actually its magnitude squared. Okay, so I can call that L squared. L squared, where L is the magnitude of the vector. If I square it, then it looks like that. So if I want to know the actual magnitude, I just take the square root of L squared, which equals L. So this L squared thing is good because I'm going to keep the square. Okay, I can always take the square root of the result, and then I have the actual magnitude. So the L squared is basically the magnitude squared. But I'm going to keep the square because it's helpful in my calculations. Okay, so don't be bothered with the square. Again, at the end of the calculation, you can always take the square root. So this L squared, I can also write in operator form in this way. L squared, the little hat, now is the same as the classical result, but now everyone has a hat on it. They're all operators. I got an Lx squared operator, an Ly squared operator, and an Lz squared operator. Now this Lz squared here, this guy, is the square of the one on top. Okay? So if you square that result, you get basically a second order derivative with respect to phi. Okay? So that is the z component. But there's also x and y components. Now, you can work this out, and we won't do that, but I'm going to show you the result. You could write out what the operator looks like. The second order derivative in terms of the angles phi and theta is this. Actually, this looks a lot like the Legendrian that we have seen. That is this capital lambda squared, which is the Legendrian, and this is essentially the same. The Legendrian is actually an operator that tells you something about orbital angular momentum, the magnitude of orbital angular momentum. the kinetic energy that is associated with circular motion on a sphere is angular momentum magnitude squared divided by 2I. And we have seen this before, actually. And now I'm going to write it in operator form. T hat and then L squared hat divided by 2I. That is now my kinetic energy. This L squared, remember again, is the magnitude of angular momentum squared. We just saw what it looks like. So now, I'm going to take this T operator, kinetic energy operator, and I'm going to operate on the spherical harmonics. Remember, the spherical harmonics are the eigenfunctions of the Legendrian squared. Legendrian squared is directly proportional to little l squared. That means that the spherical harmonics here represented in its cat form, L, ml. L and ml fully define what this function is. So L, L, ml, this function, this cat, is an eigenfunction of the kinetic energy operator because they are eigenfunctions of the Legendrian, therefore eigenfunctions of L squared. Okay? And the eigenvalues of the Legendrian were this, divided by 2I. The result is this, L, and then between parentheses, L plus 1, h bar squared. If I divide that result by 2I, that's the kinetic energy. So, that means that the spherical harmonics are eigenfunctions of little l squared, the operator. And the eigenvalues are L, and between parentheses, L plus 1, h bar squared. Those are the eigenvalues. Those are the eigenvalues of the magnitude of the angular momentum squared. Those are the eigenvalues. Okay, so I can write that out. The operator, the magnitude of angular momentum squared, when it operates on the spherical harmonic functions, those functions are eigenfunctions with the eigenvalues L, L plus 1, h bar squared. What does that mean? That means this. These functions, the spherical harmonics, their magnitude of angular momentum is quantized. That means that the particle that happens to be described by one of these spherical harmonic functions, remember the spherical harmonic functions are part of the hydrogen wave function, remember? It describes the behavior along the coordinates phi and theta, the angular coordinates. So that means that this particle, the magnitude of this angular momentum is a quantized thing, and the values are given here. Not every angular momentum is allowed. Angular momentum is quantized. That means the kinetic energy derived from angular momentum is also quantized. Okay, so those are the eigenvalues. The eigenvalues of the magnitude squared of angular momentum is of this form. We already know that the projection of the angular momentum onto the z-axis, which is not its magnitude, but it tells you something about the direction of the angular momentum, that we already know. That is ml h bar. Okay? This is the eigenvalue. Those are quantities. So when I know what L and ml are, if I know the spherical harmonics, which are indexed by m and ml, L and ml, then I know also what the magnitude of its angular momentum is, and I know something about its projection, in this case along z. So there's two pieces of information, one about magnitude, one about direction. Okay, so what about the other directions? Why do I talk about LZ only? What's so special about the z-axis, really? I mean, I could rotate in any direction, so why do I focus on LZ so much? Okay, so let's look at the other directions. And let's specifically look at X and Y, these operators, and see if they commute or not. Why do I do that? Because if they commute, that means I can know both of their values at the same time. But if they do not commute, I cannot. And this is a great exercise. I think it's in one of the worksheets or something. You can actually figure out or not whether these operators commute, and they don't, because this is not zero. Okay? The commutation between Lx and Ly is something times another operator. That's definitely not zero. What about if I commute Ly with Lz? Would it then commute? The answer is no. I get also something quite similar. Okay? In fact, I get the same constant times Lx in this case. Also not zero. And the final permutation that we can make is Lx with Ly, Lz with Lx. And the answer is the same constant times Ly in this case. So it doesn't matter what pairing I make, they all generate something that is non-zero. And that means something very important. Namely, that I cannot know the projections of angular momentum in just any direction. I can know it for z, but once I know it for z, you can see from these commutations, once I know it for z, I cannot know it for x and y, because the Lz operator doesn't commute with Lx and Ly. So once I specify a direction, let's say we specify z, I can know something about projection along z, but I don't know about Lx and Ly. It's unknown by virtue of the uncertainty principle. Okay, so we cannot simultaneously know all the components of angular momentum. So we cannot specify its direction. Pinpoint its direction exactly. We do not know that. We know something, but we know not all. Okay, so what about its magnitude then? So we have just seen we cannot know exactly its direction, but we may know something about its magnitude. So let's see if the magnitude operator, which is L squared, commutes with the projection operators. And then we see that, yes, actually these two commute, so does L squared with Ly, and so does it with Lz. Okay? So, which means that if I specify a projection along any of these axes, that if I choose x, and I say I want to know its projection along x, that has no influence on your ability to know the magnitude of angular momentum. So the magnitude of angular momentum can be specified at all times, but the projection of that momentum, angular momentum, along one of the axes can be determined at the expense of information in the other directions. Okay? So, what we can know about angular momentum in our quantum mechanical system is we can know one projection parameter, one component of the vector, one component we can know, and its magnitude we can know. So it's two things we can know about orbital angular momentum. One is, again, its magnitude, and two, one projection we can know, not three. This, again, is one of those funky quantum mechanical things, okay? This is one way to visualize that. And you have, these graphs happen to be in almost every quantum mechanical, quantum chemistry book. And it leads to a lot of confusion, like what the heck is this? So let's have a look. This graph here indicates a situation when L equals 2. Okay, so the orbital angular momentum quantum value is 2. Now, if the particle happens to have that quantum number, what does that mean? That means, first of all, that it could have 5 different ML values. It cannot have them all at the same time. It can have one of them, because the particle is in one-way function, let's say. It's either in ML -2, -1, 0, 1, and 2. Okay? So let's look at L equals 2, ML equals 2. When ML equals 2, then the projection of angular momentum onto the z-axis is ML times h bar, which is 2 times h bar, which is basically the first cone that you see there. See that the projection onto the z-axis is 2h bar. This blue angle that sits on this cone, that's the angular momentum. That's it. That's what I'd like to know. So if it points this way, what does it correspond to? It corresponds to kind of like that sphere with a line through. The line is basically the rotation thing, okay, the rotation axis. So the particle swirls like this around that axis. And in that case, its angular momentum points this way, points along that axis. Okay? But this sphere now sits this way, but I can actually walk around in x and y. Because x and y is not defined. So I can walk around like that, spin that top around like this, and trace out this entire cone. That cone is only there because I just don't have the information about x and y. That's why it looks like a funky cone. Basically, this blue angle, this blue arrow on that cone can be anywhere on that cone. I just don't know where it is. The only thing I know about it is that if I project it onto the z-axis, its value is 2h bar. Okay? So that is what I can know about its direction. I can know how long the arrow is, because that is its magnitude. So that I do know. I just don't know exactly in which direction it points. I have limited information. A little bit, which means I know the cone. That's where it has to be on, but I just don't know where on the cone it sits. Because that is what the uncertainty principle prohibits me from knowing. Now, this particle could also be, of course, in L equals 2, and now ML equals 1. Then its projection onto the z-axis equals h bar. That's the second cone. The third one is basically a pancake. What is that? That is the case for ML equals 0, which means the projection onto the z-axis is 0. It has no projection on the z-axis. Okay? So it's basically just in the xy plane somewhere. I don't know where it is. Okay? And then -1, -2. Think about these spinning tops. And the spinning top can be anywhere along this thing. Okay? That's where it sits. That's the uncertainty that I have. But that is the amount of information I can extract from a quantum mechanical angular momentum system. Okay, now, the magnitude of angular momentum I can perfectly know. Okay? The eigenvalues of L squared are L plus 1, h bar squared. Take the square root of the whole thing. That is the magnitude. If L equals 2, you just fill in L equals 2, and you know the magnitude of this angular momentum that is associated with the particle. What about its direction? I told you, we cannot know everything about its direction. And now, we have to specify along which angle are you going to investigate the system. We talk about z, but z, there's nothing special about z. If I have a sphere, the sphere doesn't have a z, really, because it's a sphere. It's the same in all directions. So I could pick any axis, really. I can pick x, y, or z. But as soon as you pick a direction in which you start to investigate, you lose the information about the other axes. Okay? So we always choose z for convenience, because it's easy for us to visualize. But there's nothing fundamental about z. It's just a choice. So we choose LZ, now we know the projection along Z, and we lose. Automatically, by making that decision, we lose the information about X and Y. It's now ill-defined. Projections along LZ are now defined, plus its magnitude, also defined. The rest, ill-defined. Okay, so I'm going to generalize this story a little bit, because it turns out all of this blah, blah, blah that I just said can be summarized in a very nice set of principles. The first principle is that in quantum mechanics, the orbital angular momentum is described by L and ML. And the values of ML are related to whatever L is. We know that. Okay? In fact, there's 2 L plus 1 values for ML for each value of L. Yes? Picture worthy, folks. Here, I'll make it even more interesting. Don't tell it to Gilman. Okay, so now I'm going to generalize this, like I said, and by basically saying, anytime I'm talking about angular momentum, the same relations that we have seen so far regarding the quantum numbers, the magnitude of angular momentum and its direction should apply to all forms of angular momentum, not just orbital angular momentum. And I'm going to show you another example of angular momentum in 2 seconds, or maybe a little bit more than 2 seconds. So instead of calling it L, because L specifically means orbital angular momentum, I'm going to call it J. J simply means angular momentum of some sort. But I'm going to keep this framework. Namely, this J relates to the magnitude. It's the magnitude quantum number of angular momentum. MJ deals with its projection. Okay? It deals with the projection of angular momentum. And so I have the same relation, J and MJ, where MJ is related to J because it goes from negative J to positive J in integer steps. And again, I have 2J plus 1 values of MJ. Remember, the particle can only be in one of these states. If it's in an eigenstate of angular momentum, it has one J and one MJ, not all kinds of MJs. MJs are just the possibilities in which it can be. Okay, so what does that mean then for the magnitude of angular momentum? Same thing. Namely, J squared is the magnitude squared operator. It has eigenvalues J, J plus 1, H bar squared. Nothing different. I just replaced the L with a J. And the eigenstates are now indicated by J, MJ. This could be a spherical harmonic, it could be something else. Now I'm letting go of that notion. I'm going to say there is a state, an eigenstate, an eigenfunction, which is indicated by J and MJ that fully defines its properties in terms of angular momentum. Because it generates these eigenvalues, which means I can know the magnitude of angular momentum from this eigenstate. I don't need to know anything about its functional form. I just need to know that it exists and that it generates eigenvalues. That's enough. That enables me to say this is the magnitude of angular momentum of this state. I can also know its projection. It is the operator JZ. JZ, come on. I never realized that. That's kind of cool. First time. This is the 7th time I'm teaching this course. It's the first time. JZ has eigenvalues MJ. MJ, come on. H bar, this is getting really crazy. The confluence of pop culture and quantum mechanics, folks. You thought it didn't exist. It's all over. You just have to look. Now, I'm going to introduce the thing that I was trying to work up against, and that is this one. Spin angular momentum. Okay? Spin angular momentum. Not orbital angular momentum, but spin angular momentum. I'm going to say spin is actually an angular momentum thing. And if that is so, it should abide by the rules, these general rules about angular momentum. Okay? I'm not going to call it J, I'm going to call it S. So S is basically the same rule that L had. S is the quantum number for spin. L, remember, could be 0, 1, 2, 3, 4. But S, only one value. 1. Always 1/2. Simple. I only have one value for S, but it's an angular momentum quantum number. It is 1/2. If S equals half, then MS runs from negative S to positive S in integer steps. There's only one step I can take. Negative half to plus half. Those are the two values. So MS can only have 1/2 plus half. This I can know just by applying the rule of angular momentum. I don't have to think it up. This is just following the rules for angular momentum. If I identify spin as an angular momentum thing, and its main quantum number is half, then that must be true. Otherwise, it's not an angular momentum. The eigenstates, then, I can also generalize. The spin eigenstates are indicated by the quantum number s, which is half, and ms, of which there are only 2. Which means that the complete set only has 2 states in it. Two states. Namely, half, comma, plus half, and half, comma, negative half. Those are the 2 spin eigenstates. I'm going to call the plus half projection alpha. That's the alpha spin state. And there's another one, which is very nicely called beta, which is half, negative half, because it has the s equals half, the projection quantum number ms is negative half. Okay, let's go on. What is the magnitude of spin? How big is the spin? Well, you have to use the s squared operator. When the s squared operator operates on one of these spin states, let's say alpha, I get s plus 1 h bar squared times alpha, because it's angular momentum. So this rule still applies. And I can calculate that because I can just plug in the value for s, which is 1/2, and I see it's 3/4 h bar squared times the wave function again, times the state again. Therefore, the magnitude of spin is this. This is the magnitude of spin. The magnitude of spin angular momentum has that value when the state happens to be in alpha. What if it is in beta? Okay, let's do the same thing. It's the same story. Because it doesn't depend on the projection, it only depends on s, and s is 1/2 for both. Therefore, if it is in state alpha or in state beta, the magnitude of spin is identical. Spin only has one magnitude, but it has 2 projections. We can also calculate the projections, of course. Let's do it. We're warmed up already. Why not? Here it is. SZ operating. I could make it even. I could say Ziza. How's that? Ziza equals ms h bar times alpha. I just watched the Emmys. That's why. Say what?
We need the Grammys.
All right, here it is. The projection of the spin when it's described in the alpha state. So when the spin particle is in the alpha state, then its projection onto the z-axis is 1/2 h bar. And if it happens to be in the beta state, then it's negative the same value. Negative 1/2 h bar. Now, if you talk to anybody on the street and say, hey, give me the values of spin, they say, well, spin up, spin down. Okay? It's kind of cute. But there's nothing spin up or spin down about this, really. It's just 2 states. If you want to describe the spin state, you just have 2 opportunities. Described by these 2 quantum values. Okay? One is basically 1/2 h bar, the other one is negative h bar, defined by its projection in space along one of the axes, in this case the z-axis. It's not necessarily a spin that spins like this or spins like that. Okay? It's kind of like it helps us conceptualize it, but from a quantum mechanical point of view, this is it. This is what spin is. We don't have to go much further than that. We don't have to think of a spinning top that spins in one way or another way. If it helps you, that's okay. But this fully defines what spin is, quantum mechanically. That's all we need to know. 1 magnitude, 2 projections, and that means that if our electron has spin, which it has now 2 things. Namely, it will be in an orbital state which is the states that we kind of figured out last time, those were all the whereabouts of the electron. Okay, the wave function is a function of space. Where is the electron at? Wave function squared tells me something about the probability density. Where is that thing? Okay, but on top of that, the electron has an intrinsic property. Namely, it could be either spin with half h-bar value or negative h-bar value, which is also part of the wave function. So the total wave function is the orbital part, x, y, and z, or r theta phi, which is the same, that's the space, times the spin, which is an intrinsic thing that has nothing to do with space. It doesn't matter where you are, you just have two possibilities of being. You can be half h-bar or negative half h-bar, independent of where you are. I think I always had an example. If you are in a car and you drive up to 55 north, 22 west, and then back on a 405 to where it hits the 55 and you go in a circle, that's your orbit. That orbit, okay, is basically your orbital state or your wave function. It depends on x, y, and z. Depends on where you are in space. But you could either drive, let's say, a blue car or a red car. That red car would be just two possibilities, and it doesn't matter where you are on an orbit or what kind of route you take, it's just that it. It's either blue or red. That's it, two possibilities. So your total state of being is defined by your orbital state, where you are, times the car color state, which is what spin is. This car doesn't switch or changes automatically, it's blue or red, that's it. If you want to change it, you have to do work. Okay? And that's the same for the electron. Once it is in a particular state, that's it. It's a red car now, it's somewhere, and the total description of its being is red times its position, and that is the total wave function. Same for the electron. Okay, I'll stop here, and little note, folks, I won't be here on Monday, but it doesn't mean I don't love you. Okay? It just means I'm not here. And so instead I will be posting a lecture video that you can watch. Please do that so we see each other again on Wednesday.